Welcome to this lesson which deals with the topic of materials. So what I want to cover today is really a very short overview of material science, specifically to convey to you that as an engineer it is fundamentally important to understand some of the basics about materials. So I'll begin with that aspect of material science, and then talk a little bit about elements and bonding, and then end with the 5 basic types of materials. So let's begin with the importance of understanding materials. If you look and think back to history of human civilization, if you pick up a history book, one of the things you will notice is that there have been periods in human civilization that are named after materials. For example, the Stone Age, the Bronze Age, the Iron Age. And the reason for that is that human progress during these periods was largely a result of humans being able to create tools out of these types of materials. So they started by learning how to create tools out of stones, and then they advanced to being able to create tools out of bronze, and finally to iron. And then, starting from the early 20th century, where concrete became one of the most important materials that we understood and learned how to manipulate. Today, one can say that we are in an era that is dominated by polymers and silicon technology. Well, silicon is the backbone of transistors that are found in every computing device, every phone, now pretty much, of course, in every computer. And now slowly it's appearing in anything that you can think about around you. Think back to our discussion about the Internet of Things, sensors, actuators, all of these contain within them transistors that are ultimately most likely powered by silicon. So today we are in the electronics era, the silicon era. You might remember this curve from our discussion of the Internet of Things as well. This is the Moore's law, which basically says that every 2 years the capacity of a transistor or the speed of a transistor doubles, or also the number of transistors per unit area doubles, and that has been going on now since 1965. So the important thing to take away here is that our progress as a human civilization is fundamentally linked to the way we can manipulate materials to our advantage. Now, that hopefully gives you a sense of why materials are important, because our progress is linked to understanding and manipulating materials. But here's another reason to think about why understanding the behavior of materials is so important. So you may be familiar with the space shuttle program, which has now ended, and of course now we are trying to send people to space using rockets from private companies like SpaceX, and so on and so forth. But till not very far back, the primary mode of space exploration for humans going into space was by launching space shuttles, and the US had a fleet of space shuttles that were routinely launched that helped us explore, for example, do experiments on the International Space Station and things like that. So one of the space shuttles was the Challenger, and on January 28th, 1986, it was scheduled for a launch. And what happened is that about a minute after the launch, about 73 seconds after the launch, which was its 10th mission, the space shuttle essentially exploded. Okay? And so the question, of course, is why did this explosion occur? Of course, rockets are very, very dangerous machines, right? Essentially, what a rocket is nothing but a solid object sitting containing the astronauts sitting on top of a fuse, and the fuse, once it lit, it basically burns a fuel like an explosion, and that's what propels a rocket upwards. You may have experienced this on a much smaller scale through a firecracker you might have let off during a July 4th fireworks, for example. So it's you can see that there's a great great possibility for danger here in rocketry, and so flying rockets are not are very very hard things to do, and so you have to really be extremely careful and have very precise engineering going on. So anyway, so the question was, why did the Challenger explode shortly after liftoff? And so a team of investigators looked into this, and they found that something very interesting was the most likely scenario for what happened here. During the evening of the launch, or the previous night when the rocket was on the launch pad, it turned out that the temperature at Cape Canaveral that night on January 28th actually dropped to one of its lowest values, and that was 31 degrees Fahrenheit. And it turned out that because this temperature was so low, there were rubber gaskets or O-rings that were being used to seal different parts of the rocket fuel, and one of these O-rings actually cracked because of the fact that it was under compression, and because of the low temperature it hardened, and it basically could not sustain that compression force, and it cracked. And when it cracked, it basically was now a leak that could not isolate the two fuel chambers. So remember, what's happening here is that fuel is being burnt in regular stages, and so one chamber burns off, and then it basically drops away from the rocket, and then the next chamber burns up, and so on and so forth. But because this was not sealed anymore, the first chamber lit up, and because of the fact there was a leak, it also blew up the second chamber, and that's what led to the explosion. Okay, so how could this have been prevented? Well, as an engineer, we want to think about every condition in which our machine is going to operate, and in that context also understand how the materials that are being used behave. So what is shown in this graph here is a plot of temperature and something called the specific volume. Okay, so specific volume is nothing but you can think of it as 1 over the volume of the material, or in other words, it's like the density. Okay, so remember, density is mass per unit volume, so specific volume is a lot like density. And what happens in a plastic material or rubber like material is that when it is at high temperature, it behaves like a liquid, but when it's cooled down, it basically hardens and behaves more like a glass. And that's what happened to this rubber O-ring. When it cooled down to 31 degrees Fahrenheit, it entered this behavior that is more like a solid or a glass. And this glass, as we know, when we it's very easy to shatter a glass, and that's exactly what happened to this O-ring under the compression forces that were holding it in place. Right? So if as an engineer, this is our responsibility. We need to understand how materials behave under different environments and choose materials accordingly so that they can do the job reliably and in a safe manner. Okay, so this is, I hope, conveying to you that as an engineer, no matter what engineering field we decide to choose, one of the fundamental subjects that we want to learn and be cognizant of is materials science and engineering. And that's why you will find that every engineer takes a basic undergraduate class in materials science and engineering. Okay, so now let's go on to some aspects of material science and engineering that start connecting you to your basic science learning in high school, maybe in chemistry or in physics, to the material science that we want to learn as engineers. Okay. It all begins by understanding the periodic table, which in turn comes from understanding the atomic structure. The atomic structure is the picture that you want to start out with is by thinking about a shell of a fuzzy shell that contains electrons that surround a nucleus shown here that contains a neutral particle called the neutron and a positively charged particle called a proton. Right? And so think of this as an analogy. You can think of the solar system. The sun is our nucleus, and each of the planets around it, they form different shells or orbitals around the moon, around the sun, and so those are analogous to the electrons in an atom. Okay. So the nucleus consists of n neutrons and z protons, and in a neutral atom the shell consists of z electrons, and that means you have an equal number of protons and electrons, and the atomic mass number of the atom A is given by the sum of the neutrons plus the sum of the protons. It turns out the electron mass is so small that you can neglect it in relation to the mass of the neutron and the proton. Okay. In the periodic table, we know that these elements are arranged in a way of increasing number of protons, and so it is periodic because elements are arranged in this order where you're increasing the number of protons of the atomic number by adding protons to the shell and an equal number of electrons to adding protons to the nucleus and an equal number of electrons to the shell, right? And so each column here is known as a period, while each row is known as a group, right? And so hopefully you have some background with periodic table, so I'm not going to spend too much time here other than just emphasizing that it's an important starting point in the understanding of some of the fundamental concepts in material science. Now, the periodic table has about 118 elements, as you can see here. Many of these are not very useful because they are radioactive elements. So typically, we have about 100 elements in the periodic table that realistically we can use for everyday purposes, and those are non-radioactive and are easily available and are not prohibitively expensive, right? So how do all these elements come together and give us the useful materials around us? So let's begin with this question here. If I ask you to guess how many different elements you could find in a typical smartphone, what would your immediate guess be? 5, 10, 50, 100? Well, if you guessed 50, you would probably be you'd probably be close to the correct answer. There are about 41 different elements being used in a cell phone, and it turns out that that each of these elements can be contributing to one or more functions in the cell phone. Okay? So the way we think about the elements that appear in the cell phone are based on the kind of materials they contribute to, and that is where we now want to think about the 5 basic types of materials that one finds around us, right? And these are metals, ceramics, polymers, composites, and advanced materials. And this is what I'm going to talk about next, what each one of these are. But before we get to that, what we need to understand is, why are these materials different? Why is a metal different from a ceramic? Why is that different from a polymer, and so on and so forth? And in order to understand that, we need to understand something known as bonding. So let's begin with this example here, and this is the gecko, which is a little lizard that you may have seen either in a documentary or an advertisement. For example, the insurance company Gecko really was inspired by the gecko. The name Gecko was inspired by the gecko, and the gecko is famous because it has this amazing ability to stick to a surface. So you may have seen it hanging upside down from the roof, and it can support its own weight. But also what's amazing is that unlike a regular glue that we use to stick objects together, this gecko can instantly detach and run pretty fast, right? So it has a very unique type of glue associated with it, or a sticking ability associated with it. In fact, it doesn't have a glue, but it has a force, a sticking force. It turns out that geckos are inspiring a whole field of robotics that is related to being able to develop robots that can climb walls and stick to walls and so on and so forth, right? So how does this gecko achieve its amazing abilities? How does the gecko stick and unstick? Well, in order to understand that, what scientists did was put the gecko feet under a microscope and look at its structure. And what they found is that when they looked at the gecko feet and they magnified it about 1,000,000 times, they found that the feet essentially consist of tiny tubes or hair-like structures whose diameter is of the order of 10 to 100 nanometers. So these are nanostructures. You can think of these as a tiny hair that make up the feet, and each of these hairs has a diameter of about 10 to 100 nanometers, and there are millions and millions of these packed into their feet. Now it turns out that each of those nanostructures, it exerts what is known as a van der Waals force on the wall. And so when you take one nanostructure, its force is extremely small, but when you combine millions of them, it adds up to a fairly large force that can easily allow the gecko to, basically stick upside down onto a surface and carry its own weight. But now when a gecko wants to move, it basically sends an electrical signal that changes the angle of these fibers with respect to the wall, and that allows it to instantly detach and move on the surface. And so that's one of the amazing reasons why the gecko behaves the way it is. Okay. So what I wanted to convey here is that what you're seeing is something that is fundamental to material science, and that is understanding how things bond together and how their structure is actually what the structure actually looks like under a microscope are two of the critical aspects that determine how a material behaves. So with that, let's go on to understanding now this idea of bonding in a more quantitative sense, in terms of what actually happens between two atoms or two molecules. Well, the first step of bonding you encounter is something known as the primary bond, and these are strong bonds. So when two atoms come and attach and join to each other, if they are joined together by primary bonds, then these are pretty strong bonds. And remember our topic of energy. Well, these bonds are of the order of 100 to 1000 kilojoules per mole of atoms or molecules. Remember, 1 mole is equal to 6.023 into 10 to the power 23 atoms, right? In order to break apart these 6 into 10 to the power 23 atoms, if they are bonded by a primary bond, you will need somewhere between 100 to 1000 kilojoules of energy. Okay? So that's actually quite a lot of energy. Now, there are three main types of primary bonds, and that's shown here in the figure here. We have the ionic bond, a metallic bond, and the covalent bond. And so let's take a moment to understand how they are similar or different. Okay? What happens in an ionic bond, what happens in an ionic bond is that when two atoms come together, an electron from one atom is actually transferred onto the other atom. So one atom becomes positively charged because it has lost an electron, while the other atom becomes negatively charged because it has gained an electron. So an example of this is sodium chloride or common salt, which is NaCl. Here sodium becomes positively charged and chlorine becomes negatively charged. Okay? So that's an ionic bond. Now, what happens in a covalent bond is that, unlike an ionic bond, where an electron is completely transferred from one electron to the other, in a covalent bond, the electrons actually come and occupy a space between the two atoms, and so they are shared equally by the two atoms, or maybe not equally, but they're shared by both the atoms. And so the covalent bond is something called the electron sharing bond. And examples of these are carbon and diamond and the water molecule. Okay. The third primary bond is the metallic bond, and this one is unique in the sense that what happens is that electrons from an atom in the metallic bond basically is shared by all the other atoms in the solid. And so you can think of the metallic bond in a visual sense in the following manner. Think of a tank of water, and inside this tank of water you basically create a structure that is a bunch of tennis balls glued together, and you create a three-dimensional arrangement of those tennis balls, and think of those tennis balls as the nuclei of the atoms. And so now the water surrounding the tennis balls is like the electrons surround the atoms in a metallic structure. So those electrons now cannot be identified as belonging to a single atom, and in fact they are shared by all the atoms. Okay? And so this is a bond that is also electron sharing, but the electron is shared by all the atoms, as compared to a covalent bond where the electrons are shared by only the neighboring atoms. Okay? So to summarize, in an ionic bond, you have electrons are transferred to neighboring atoms. In a covalent bond, electrons are shared between neighboring atoms, while in a metallic bond, the electrons are basically free to move around, and in a sense, they're shared by all the atoms. The next type of bonding is the secondary bonding, which is much weaker, and you can see that for 1 mole of atoms or molecules, the strength of the bond is only 100 kilojoules or less. So this is a factor of 10 to 100 times smaller typically than a primary bond. And the way these bonds work is by the formation of something called electrical dipoles. So an electrical dipole is basically a system in which there is a separation in the center of the positive charge and the negative charge. Okay, so when for example, I take a tennis ball and I squeeze it and make it an oval shape, and you can think of that oval shape as really representing the net charge distribution inside the tennis ball. It now has one side being positive and the other side being negative, and this is called a dipole. And you can have a system which is a permanent dipole, for example a water molecule, or you can have dipoles that are fluctuating with time. So every atom is basically a fluctuating dipole, and so every atom can undergo these kind of weak secondary bonds, which basically can bond together any two atoms or any two surfaces or any two molecules if they don't have one of the primary bonds available to them. Okay, so whenever there is an absence of a primary bond, there is most likely going to be a secondary bond due to the presence of these dipoles, and these ultimately lead to bonds of the energy of much less than 100 kilojoules per mole of atoms or molecules. Okay, so with that introduction to bonding, now let's move to our final topic, which is the 5 types of materials. Okay, so let's begin with metals. Now metal parts you're already familiar with. For example, think of a spring. Think about your automobile parts. Think about a bicycle. You'll find that there are parts there that are pretty hard. They feel cool to the touch. They are reflective. And when you knock on them, they make a ringing type of sound, a very metallic type of sound. And so metals are those elements or compounds that tend to have metallic bonding. So remember, metallic bonding is one in which the electrons are shared by all the atoms in the solid. Now the result of the metallic bonding is that metals tend to be mechanically strong and ductile. That means not only are they hard to deform, but they can deform quite a bit if you apply enough force, and so they are ductile. That means they can bend or elongate, but they are not easy to break, right? So they are very tough, and that's one of the biggest advantages of a metal. They can be changed into different shapes, but they can't be broken very easily. Metals tend to be electrically conductive. They also conduct heat very well, so they are thermally conductive. They do not transmit light. That means they are optically reflective, and this is something that you might have experienced. For example, think of an aluminum foil that you have at home. It does not transmit any light through it. It reflects all the light. And from the perspective of magnetism, metals tend to have a range of magnetic properties. For example, iron is one of the most well-known magnets, while something like copper or aluminum are not magnetic. And finally, the sixth property that is one of the fundamental properties is their chemical reactivity, and metals tend to be quite chemically reactive. So what we have laid out here are 6 of the fundamental properties of materials: mechanical, electrical, thermal, optical, magnetic, and chemical. And so every metal or every element or every compound can be categorized on the basis of these 6 properties especially if these are solids that we are talking about. Okay, next let's move to ceramics. I think the most common ceramic that each one of us have experienced is a coffee mug or a glass drinking cup. Okay, so glass is a ceramic, and ceramics have some very unique properties, including the fact that they can be exposed to very high temperatures, as you may know from your baking containers, which you can use glass vessels. Also from the viewpoint that you can put things in the microwave that are of glass. And so ceramics are very, very useful class of materials, and it turns out that ceramics tend to have ionic bonding. And so that means you have elements or atoms here in which one atom is negatively charged while the other is positively charged, because there's a transfer of electrons from one to another. And by the way, for us as a since we are thinking about ionic bonding, a ceramic is also sodium chloride, which is common salt, and that also falls into the category of a ceramic. Now ceramics in general, they tend to be very strong, but they break very easily. And so when you think about glass, you know that glass is very strong, but it can also shatter. Ceramics tend to be electrically insulating. That means they do not carry current. They're also thermally insulating, as you may have noticed from the kitchen utensils around. They can be optically transparent. They can have a range of magnetic properties that range from being magnetic to non-magnetic, and they generally tend to be chemically non-reactive. So again, remember the 6 basic properties that we are looking at. And so ceramics vary quite a bit from metals, especially in their chemical reactivity, electrical properties, thermal properties, and optical properties. And the fundamental difference between a metal and a ceramic in terms of its mechanical property is that metals tend to be ductile. That means they can bend and don't shatter, but ceramics are not ductile. And are very brittle, so they can shatter easily. The third class of materials is a polymer, and a polymer is all around us in the form of plastics. So you can think about virtually any object around us that we have access to. Think about the clothes we wear, the shoe we put on. These are all made of different types of polymers, right? So polymer is a material that tends to have covalent bonding, and in this particular case, what it leads to are materials that typically are mechanically very weak, and as you can see from the plastics around you, they're not used for very intense load-bearing applications. And these polymers also tend to have a ductile behavior. That means they can be stretched a lot, which you might see from for example, a plastic bag that you might get from the grocery store. It can extend a lot before it actually breaks. The other 5 properties, it's electrically insulating, thermally insulating, optically transparent. Typically they are non-magnetic. It's very difficult to make magnetic polymers, and they also tend to be chemically non-reactive. So one of the advantages of polymer over a ceramic is that polymers tend to be extremely light, and also they tend to be ductile, so they don't shatter very easily. Okay, so type number 4 is a composite. Well, a composite is basically a material that is made up of a combination of the 3 basic materials we just discovered or just talked about, which is a metal, a ceramic, or a polymer. So you can have a matrix which is made of a metal, and have a dispersed phase which is made of a ceramic, or any combination of the two, any 2 of the 3 types of materials can be put together to form a composite. The idea of a composite is really you want to achieve some properties that you can't achieve uniquely by either using a ceramic or a metal or a polymer by itself. And one of the major advantages of a composite is that you can usually get extremely low weight materials, but they have very high strengths. That means high mechanical strength. And the applications here are basically numerous, from aircraft body to car car parts to musical instruments, um, to for example, the turbine blades in windmills, and structures that can even be used in bridges, and of course in cell phones, right? So composites have properties that span a wide range depending on what two or more materials are mixed together. Finally, advanced materials form a whole class of different types of materials that basically are quite unique and cannot be put in one of the four previous classifications. Right? So here are the four basic types of advanced materials. The first is something known as a semiconductor, and a semiconductor is basically at the heart of every chip that we have in our computer or a cell phone. And in a semiconductor, the basic idea of a semiconductor is that it's used in logic devices to turn on and off signals. And the reason you can do that is because its electrical properties can be controlled, and these electrical properties typically lie between that of a conductor like a metal and an insulator like a ceramic. The next type of advanced material is the biomaterial, and these are materials that are compatible with the human body, so that you can actually replace a part in the human body with this artificial material, and the body will not reject it because of toxicity and other factors. We have already talked about the Internet of Things, and these you can classify them as smart devices or smart materials, because you have now created a machine or a device that is able to communicate and perform certain activities in response to environmental changes. And then there is a class of materials called nanomaterials, in which the dimensions of importance in the material are less than hundreds of nanometers, and this introduces unique and exciting properties of the materials. So as a whole, these four types of materials come under the classification of advanced materials. And as you can see, they may be made of one or more of the basic types of materials we talked about, which is the metal, the ceramic, and the polymer. Okay, so with that, I'd like to wrap up this lesson. Please make sure to go through the additional reading content in the form of a PowerPoint or PDF file that I will upload, and follow up on any other activities that are related to this content. Thank you.